Welcome back, everybody. We noticed that we didn't record in the first hour, so you in the lecture hall and you on Zoom will have been the only people ever to have seen this lecture. So I'm just going to redo it in the next hour, and that way no, I'm joking. We could just continue. So where were we? We had the observation that you made, and that is correct, that we could add weights to foo, to bar, and to foo bar. And that should improve the problem that we have here, which is that bar is rare, and it's not doing justice to B that it's not the first document, right? Because we should have more weight on bar. So your remark is absolutely correct, and this is what we are going to do now. So what kind of weight could we use? Well, you might think of the collection frequency. That is the number of times that a term appears in the collection. That's how rare it is, right? Or how frequent it is, right? So for example, if we look at this collection of 3 documents and at the 3 terms foo bar and foo bar, we notice that term foo appears 4 times in the entire collection. You see, it's 1, 2, 3, and 4, right? So that's 4 times. Bar appears 5 times, 1, 2, 3, 4, 5. And foo bar appears 5 times, 1, 2, 3, 4, 5, right? So that would be what we call the collection frequency, 4, 5, and 5. Who has already seen the collection frequency somewhere? Who has seen it in this lecture? Yes, you have indeed. We saw it here. Yay, one less thing to learn. That's again the same thing. When we were actually looking at Zipf's law and sorting the terms by decreasing number of occurrence, we were actually referring to the collection frequency, right? So by decreasing collection frequency, that gives us Zipf's law. So now that we know we're just using something we also already knew, we could have a few objections to this way of computing the weights with the collection frequency, because in that case, the most, or one of the most frequent terms is foo bar, because it has 5. That's the maximum number of times it appears in the collection compared with other terms. However, what do you notice about foo bar? It's all in one document. It's in document 2. So what you probably are looking at here is maybe this is a highly specialized term that only appears in specialized books. And so probably book number 2, document number 2, is some document on foo barology, right? And it's specializing into explaining foo bar. So maybe foo bar is actually rare, right? Maybe it is actually a rare term, because even though in the specialized book on foo barology, it appears all over the place, but there's only a few books that actually have this term. So maybe that's still not entirely satisfying, right? Maybe the collection frequency still is not the way to go for the terms. But still, you know it's called collection frequency. You know that's the same as in Zipf's law. And so you can compute. Who could compute collection frequencies? If I give you other collections, other documents, who would be able to do that? Okay, very good. What could we use then? Not to weights, not the collection frequency. What other frequency do we have? Anybody on Zoom? Yes. The document frequency, exactly. We are going to use the document frequency. That is the way to go. So the difference between the document frequency and the collection frequency is that now we are not counting the total number of occurrences in the entire collection. We are counting the number of documents in which each term appears. So it means that in that case, foo, even though it appears 4 times in the collection, appears in 2 documents, documents 1 and 2. Bar appears in all 3 documents, 1, 2, and 3. So its document frequency is 3. And foobar appears in only 1 document, very rare. So its document frequency is 1. Something incredible is that you have also already seen the document frequency right here. These are the purple boxes in the standard inverted index, right? So the term frequency, the collection frequency, the document frequency, we are just linking it to other parts of the lecture where you've seen them. So they are not new for today, but now we put them, the 3 of them together in the perspective of ranked search, all right? So these purple boxes are document frequencies. What can we say here? Well, we can say that foobar is very rare. Actually, that's the rarest that you can have. Well, you could tell me, okay, 0 would be even rarer, but if it's 0, you don't even see it anywhere, so it wouldn't even be in your index, right? So 1 is actually the rarest. And then bar is the most frequent of all. In fact, bar is probably a stop word. It's probably V or A or is or B, so some word that is very, very frequent. And foobar is probably a very rare term, like, I don't know, sesquilinear, right? So it's very, very specialized terminology. Okay. But for the weights, that's not exactly it, because we could use the document frequency as a weight, but do you see here that if the document frequency is very high, we would like the weight to be low, right? So the direction is not right. The direction of the document frequency is not right. We need to inverse that. And we need to literally inverse that by taking the inverse of it. So we are going to do 1 over the document frequency, and then the order is right. But we are still going to do a bit of tweaking right here. So not just 1 over, but we are in fact going to take 3 over the document frequency. It's just some kind of renormalization, because then it's between 0 and 1, right? So 3 over. Why 3? It's not a magic number, it's the number of documents, right? I just count the number of documents, and then I take the number of documents divided by the number of documents in which a term appears. So now, if 3 over the document frequency is 1, then it means it appears in all documents, right? So that's that's basically a frequent term. And if 3 over the document frequency is equal to 3, it means it appears in only 1 document, right? So it's higher. By the way, I said nonsense. It's not between 0 and 1. It's 1 or more, right? It can go all the way. It's between 1 and the total number of documents. Okay, who agrees with that? All right, so now it's in the right direction, right? We are going to have a very low n over df in the case of the frequent words, and a very high n over df in the case of rare words. But we are going to do one more thing. We're going to take the log of that, just the logarithm, to remove a bit of that, the influence of very high numbers. Why? Because if you have a document with 1,000 times the term and another one with 2,000 times the term, probably you don't want to make a difference of 1,000 between the two, right? The difference between 0 and 1,000 is enormous, right? Not having a term at all and having it 1,000 times, that's a huge difference. But having a term 1,000 times or 2,000 times, that's no longer a big deal anymore, right? That's what the log does. The log is going to amplify the differences from nothing to something or small numbers, and disamplify the differences between very high numbers. So log of n over df is the formula for our weight, and that has the magical name of inverse document frequency, also known as IDF. Who has already seen IDF? Right, you might have seen it. So it's or TF-IDF. Maybe some of you, all right. But I'll come to that. So inverse document frequency, IDF. Something that I also insist on, because we have term frequency, collection frequency, document frequency, So it's easy to confuse them. A reminder that the term frequency is bidimensional, depends on the term and the document, but the collection frequency and the document frequency are unidimensional. They only depend on the term. They do not depend on the document because it's aggregated over the entire collection. So DF only have a subscript with T and not with D, right? The same for IDF. It only depends on the term. So this is one-dimensional. And this one-dimensional gives us exactly what we want. We have weights for our terms. So let's go back to where we were with the example that we wanted to improve with foobar and foobar, who are right here. And now we have our weights that we computed. So you see how I computed them, right? So this is 3 by 2, that's 1.5. We take the log of that. 3 by 3, that's 1. And the log of 1 is 0, right? And then the foobar 3 over 1, that's 3, and the log of 3 is 1 over 1.1, right? So if you take the log, now it's no longer 1 or more, it's 0 or more when you take the log of 1 or more. All right, so I have foo, bar, and foo bar, and you see that the world is in order because foo bar is, foo bar is, what did I do here? What kind of, I think I probably just generated new numbers that have absolutely nothing to do with what we have here. Anyway, just forget that the previous example, maybe I should redo the slides by taking the same numbers. But anyway, I just made up some numbers in there that have nothing to do with the previous slide, and that gives us foo bar and foo bar. And I did it in such a way that bar, which is rare, has a very high inverse document frequency. We give it more weights. So foo has a weight of 5, bar has a weight of 10, and foo bar has a weight of 3. And what I'm going to do now is multiply horizontally. I'm going to multiply every line in here with the corresponding number in there. So all multiplied by 5, that's 25 and 5. Then line 2, I multiply everything by 10, so that's 0 and 40. And line 3, I multiply everything by 3, so that's 6 and 3. Who agrees with that? Now, quick question. If I gave you a collection of terms like displayed like this, like what you see on the left, and I ask you to do that, to basically compute the term frequencies, the IDFs, and the product, who would be able to do that? Right? So you can try it as an exercise, but it's very mechanical, right? That's just what we do with this. So now we have multiplied TF and IDF, and that gives us what we call the TF-IDF, right? And that's something you might hear. A lot of people say TF-IDF as almost a new word. They basically mean the weight of the terms and document pairs based on the term frequency and the inverted document frequency. That is how they will contribute to the score. Higher term frequency contributes higher. Lesser document frequency contributes higher. So now, if we want to now compute the score, we just compute the sum. So we have a total of 31 for A and a total of 48 for B. And now B is winning, which is what we wanted, right? Who understood what happened and now why suddenly B is winning now, right? It's these weights that changed the thing. So now we consider that if a rare term occurs in a document, that is a big deal, right? So we want to put more weight on it. So that is known as the TF-IDF scoring system for information retrieval. Okay? But now the difficulty is to implement it. Because it's one thing to do the math and to put numbers on a slide, but it's another thing to actually implement that in real life, because we are going to have billions of documents, maybe trillions of documents, maybe not of documents, maybe trillions of tokens, and millions of terms, right? So there is one thing that I keep telling my master students is that before rushing into the implementation of that, which might be very tempting now because you know how to do it, you have to sit back a little bit and think about it. What better way to think about something than to do some mathematics, right? So now we are going to look at it mathematically and try to abstract a little bit with the power of mathematical structures. And we are going to invoke a mathematical structure that I assume you have all seen in linear algebra, which are vector spaces. Who already saw vector spaces? I assume all of you, right? Okay. So in the old system, we had documents that are lists of words, but we abstract them and simplify them as sets of words. And we saw that with this set of word semantics, we can see documents as vectors of Booleans, right? Now we saw, and that's for the advanced knowledge that for those of you who were bored, I put in the Moodle that this is not technically a vector space. It's more like a module, because then it's not a ring. It has less of a structure, but you can still make the vector multiplication and the matrix multiplication work. So it's not exactly a vector space, but can be manipulated like them, right? So basically we have vectors of Booleans. So they look like this. So here I just put it horizontally, but it's maybe more usual to put the vectors vertically. So the idea is that we have terms or words. I just use them a bit interchangeably right here, terms and words. Every position right here in my vector space, every coordinate corresponds to one term. Maybe this is computer, this is information, this is ETH, this is system, this is Zurich, this is retrieval, this is sesquilinear, and this is foobar, right? So this gives us a vector of Booleans, set of word semantics. Now, if we think a little bit, now this is a document, it contains 4 terms, right? What if we consider the single term, just one term? Do you agree I could represent that one term as a vector, right? I would just put zeros everywhere and just a 1 that corresponds to the term that I'm referring to, right? Now, where would they be in the vector space? These vectors that have zeros everywhere except a 1 somewhere. Do you visualize them in your head? Try it in 2 dimensions, 1 dimension, 2 dimensions, 3 dimensions. Probably you saw something like this, right? In 2 dimensions. I have 0, 1. And I have 1, 0. Now, if I generalize that to 3 dimensions, it looks like this, right? I have 0, 0, 1, 0, 1, 0, 1, 0, 0, right? So it looks like a triangle now. So now it would be just a line. Now it's a triangle. Who actually knows the generic name for that? If we go to higher dimensions, how triangles are generalized? Have you ever heard of that? Start with an S. Simplex, exactly, that is the word. It is a simplex. So in fact, terms can be seen as the vertices of a simplex. A simplex is just a triangle, but generalized to higher dimensions. Right. All right, I have this, yeah, that's it. So if you want to visualize simplexes, they look like this. So I didn't do that, I took it from Wikipedia. Give the credentials here. So dimension 0 is just a point. Dimension 1, it's a line. Dimension 2, it's a triangle. And dimension 3, it's a tetrahedron, right? And then you can imagine in higher dimensions. So that is called a simplex. All right, so terms would be the vertices of a simplex. Now, what about documents? Where would the documents be? So that would be the terms. You could also consider that the documents containing exactly one term would basically be here too. But what about general documents that could contain any number of terms? Where would they be? Not on a simplex, but where? That would be more than just the simplex. If you can directly give me the fancy name for that, that would be amazing. Let's see if you figure it out. Where would the documents be in the Boolean setting? Vectors that have zeros and ones, basically. Imagine it in 2 dimensions, 3 dimensions. Who sees it? Who sees it and is too shy to answer, and I promise I will not ask? Not even that? Okay, let me show you then. Let me show you. So that is an example in 2 dimensions. 0, 1, 1, 1, 1, 0. I could have put 0, 0. I mean, that would be the empty documents. If you're strictly speaking a mathematician, you do want to consider the case of an empty document because all the special cases are important. So I could even have put 0, 0. But where are they in 2 dimensions? They are basically the vertices of a square, right? In 3 dimensions, now you see it's a hypercube, right? I just put 4 of them, but there would be 8 of them, right? Do you see that it's a hypercube? It's the vertices of a hypercube. So this here is where my documents are if I use vectors of Booleans, right? Individual terms, the simplex, and the documents in general, they would be on the vertices of a hypercube. So it's good to visualize that, right? To start visualize that in space. Okay. That is the for visualizing simplexes. I think for hypercubes, I don't need to do it because it's something maybe more natural, right? That would be a dot, a line, a square, a cube, then a hypercube, and so on. Okay. So having said that, that was the vectors of Booleans. Now, we are going to go ahead and use bags of words instead of sets of words. And the thing that changes is that now my documents are vectors of numbers, not just necessarily 0 and 1, but any numbers. Now, you might wonder why decimal numbers, because if it's a bag, this would just be integers, right? But we'll see how it can actually be real numbers because we are going to renormalize. So that's where these decimal numbers are going to, real numbers are going to come from. But basically, we have documents that are now vectors of numbers, right? Any numbers? No, right? Just real numbers and non-negative. I'm not going to have negative numbers in there. Do you visualize all of these vectors that only have non-negative coordinates? Do you visualize it in your mind? Right? That would be, so we go from here to here, that would be the first quadrant of a real vector space, right? In the plane, that would be basically the top right part, but you can generalize in 3D, 4D, and so on. Who sees that? Right. Technically, that is also not a vector space. If you just take the first quadrant, it's not a vector space. It's a module, again, because then it's R plus, so that's not a ring, it's a semi-ring. But what interests us is you can still do matrix multiplication, scalar products, and so on and so on. So this is why we don't mind that it's only the first quadrant and that it's not the whole vector space. All right. I wanted to show that slide. So we said, yes, we go from Booleans to numbers. And what numbers are we going to put in there? We are, in fact, going to put preferably the TF-IDFs that we've seen earlier. Now you know why it's not integers, because the TF-IDF can be any real number, right? Because we took a log somewhere, logarithm, plus an inverse. Who sees that? That because it's TF-IDF, it's not going to be just integers. But I should emphasize one thing. Even though TF-IDF is the most popular ever, that's kind of the textbook way of implementing such a system, it's not the only one. There are other ways of putting weights in there, and I'll show you at the end of this lecture, probably next week, the other ways. But I'm going to use, for the purpose of this lecture, TF-IDFs, because that's easy to understand. I already explained it to you. So yeah. Some people might do it with just the term frequencies, for example. They might not want to multiply with the IDF. Some people don't want to take the log, and so on and so on. Okay, so now that we have seen that, we are now visualizing our documents in the first quadrant of some vector space of as many dimensions as terms. You know it's big M, right, for the number of terms, so it's R to the power of M. And yeah, so just the first quadrant. Now you can see them as points or you can see them as vectors, right, in that vector space. So now I hope you see the power of that, because technically what we did is we had books that you just hold in your hands that have words in there. And now these books, we abstracted them away so much that these are just vectors in some vector space. Right? That's the power of abstraction. Now we have our documents there, and we can start manipulating our documents and our querying system with that vector space and with these vectors. So I'm going to, yes, I'm going to use the as many coordinates as terms, x1, x2, all the way to xm. I put a little arrow on top of x. In the literature, you might also find them in bold instead of the arrow. It's just a matter of convention. And so once you have a vector, one of the first thing you want to do, I mean, I don't know you, but what I want to do is compute its norm. Like how far away it is, yeah, it's a weird thing to do. But anyway, let's compute the norm of the vector. And here, we already saw the dot product a bit earlier that now I know you know. If we do the dot product of it with itself, and then we take the square roots, that is actually a norm that is known as the Euclidean norm, right? And that you've seen before, right? You know the Euclidean norm. It's not the only one. There's other norms. You could say, for example, the sum of the absolute values of the coordinates, or you could do it with the cube instead of the square. You could also take it to infinity and take the max. I mean, there's plenty of ways to do that, but this in particular is the Euclidean norm. All right, so that tells us how far away it is from the origin. So now that I have taken the norm, I can renormalize my documents and bring it on the unit sphere, right? So it means that whatever document I have, I can bring it to the unit sphere. So now what's new is that instead of having documents on my hypercube vertices, now my documents are any points of the unit sphere of my vector space. That is 2 dimensions. It's just a circle. In 3 dimensions, it's a sphere. And then in higher dimensions, it's just the generalization of that, right? All the vectors that are at a distance of 1 of the origin. Okay, so I renormalize them. Now, several things. The first thing is, why does it make sense to renormalize the document? Because in a way, it would mean that the norm of a document doesn't matter. What matters is the orientation of the vector, but not the length of the vector. Can anybody think of an intuitive argument on why the norm of the vector doesn't matter? Okay, then let me give you an example. Imagine that I take, I don't know, a book, let's say Deception Point by Dan Brown, and I do something illegal, meaning that I copy it over and over and over. I just write a new book that has 10 times the entire contents of Deception Point. And then I do it with 100 times, 1,000 times. And now I sell to you, well, I shouldn't be doing that, but anyway, let's do it with something that is not copyrighted, like Sherlock Holmes. I take Sherlock Holmes, print it 100 times, and then I put it for sale. Do you think anybody is going to buy that? Is there any added value of printing it 100 times instead of just once? There is none, right? It's exactly the same thing. There is absolutely no added value or information by just duplicating the book. Who sees that the original book and the duplicated book corresponds to 2 vectors that have the same direction? They just differ by a scalar factor. That's what happens. So you can imagine that this renormalization thing is more like just if you duplicate or deduplicate the book. If you think of it, the direction of the vector tells you how the terms are frequent relative to each other. You basically remove the absolute values of the number of terms. It's just the ratios of how the terms appear, right? So that's how you see it. If you multiply the vector by a scalar, that's the duplication of the book. And if you just normalize it, of course, you cannot deduplicate a book, or maybe it would be impossible to read, but basically you get an abstract representation of the book that forgets the absolute values and just keeps the relative frequencies. For whom is that clear? So it means that normalizing in this way actually makes sense, right? The second thing I want to say, just to be complete, pun intended, when we have an inner product like that and a space that is complete, do you know how it's called? Starts with an H, a Hilbert space, the same ones we have in the quantum physics. So we are in here in a Hilbert space, and we are living on the unit sphere of a Hilbert space. This is where our documents are. Concretely, if you take the TF-IDFs, you do one more step after the TF-IDFs, you compute the norm and divide, so you renormalize, and then you get something that looks like this. You can check. I think this one I did, actually, I computed it. I'm not sure anymore, but normally the norm should be 1. Okay, so now we have our documents on the unit sphere. What are we going to do now? We are going to pursue this intuition. When I said if I duplicate Sherlock Holmes 100 times, it's actually keeping the direction of the vector, but just changing its length. Who would agree then that if I duplicate a book and renormalize, that will be the same point on the unit sphere? Right? If I give you a Sherlock Holmes and then duplicate it 100 times, it's the same point. What that tells us is that the same point on the unit sphere is basically equivalent documents. They are essentially the same. Not exactly the same, but essentially the same. Now, what characterizes a point on the unit sphere? Do you agree it's more or less only a matter of angles, right? Who has already seen polar coordinates? Right? So in the plane, for example, if you take a complex number, you can express it as r times e to the power of I theta, right? Then you can have the radius and theta, the angle. You can do it in 3D. Then you also have the length, and then you have, you typically use phi and theta, right? So phi tells you how it rotates like this, and theta is from the North Pole, right? Just like longitude and latitude on the Earth. So what I want to say here is that if we remove the length out of the picture and we look at polar coordinates, we are looking at angles, phi, theta, and whatever angles make sense in higher dimensions. But more precisely, if now I look at 2 documents, not just 1 document, but 2 documents, do you intuitively see that the angle between these 2 documents are going to give us information of how similar these 2 documents are? Right? This is the intuition, the angle between the 2. Now, how do we compute the angle between 2 vectors in a Hilbert space? Or let me help you, the cosine of the angle. Yes? Exactly, we take the dot product, and the dot product of the normalized vectors is going to give us the cosine of the angle. So the dot product, that's the same formula. We've seen it so many times today, the dot product. So if we renormalize the vectors, the dot product gives us the cosine of the angle. Who agrees that you know, right? You should know from before. Okay. So that's great because now I can just do some math, you know, some cooking recipe out of vector space and Hilbert space magical formulas. And it spits out some number that tells me how similar documents are. It's magical, right? If I just give you the original books, you cannot do that, right? I give you Sherlock Holmes and Dan Brown and ask you what's the distance between these, you cannot tell me, right? But if you convert these books with their contents to the vector space and you compute the dot product, now you can tell me. So there is a number out there that tells us how similar Dan Brown and Sherlock Holmes are, right? So that's the power of math, and that's exactly what we need for information retrieval. So the cosine of the angle we get with the dot product. So now we start seeing that it's the dot products of the vectors that are going to be important to us in here. So that gives us the similarity between the 2. I don't actually, if similitude actually exists in English. Maybe it does. Similarity. So intuitively, these 2 documents are very similar, right? Because they get normalized to almost the same point on the unit sphere, very small angle, and these are very different documents. Who agrees? Okay. But now I'm going to go an extra step. Because not only the documents are vectors, but if you think about it, queries are vectors too. If the query you enter is just like in Google, you just enter a few words, even in natural language, like when you copy-paste an error message, my query is a vector. The same in an LLM. If you write in ChatGPT, that ends up at a vector. So now, that's actually now bringing us closer to that direction, and maybe you start seeing where this is going. If my documents are vectors and my queries are vectors too, do you see it? Do you see how I can now execute the query and give you the results? Who can tell me? Normally, you should already have everything you need to answer that question. Who can build a system? You see any raise hands? Anybody? On Zoom? Who knows how to build it, but is too shy to tell me? Okay, but I promise I will not ask. When I ask that, I don't actually ask, because otherwise you will no longer raise your hands if I ask it again. All right, but I know you know. I know some of you know what you mean, so I'm going to get to it. So now I put the queries as yellow and the documents as blue, but now it's very powerful because I'm saying the queries and the documents, these are the same things mathematically. These are just vectors in some in the first quadrant of some vector Hilbert space. All right, and now you see, if that is the query, the yellow point here, then probably this document right here is going to be top in the rankings, right? Why? Because the angle is very small. Remember, it's the angle, not the distance, right? I'm interested in the angle. If you renormalize everything, they will be almost the same. Who sees the results of that query? If you have to rank them, who would be able to give me the ranked results, right? Probably then next would be, oh, I need a bit of, I have it right here. We can figure it out. Who is next? I have this right here. So let's try. So we need to, oh no, it doesn't project on the screen. Oh, that's sad. I was hoping that somehow it would actually, if I put my, yeah, I can know roughly where it goes. So like this, the line, I just want to see who wins. I think D5 wins. Who agrees D5 wins over D4? So we have D3, we have D5, then we have D4, then we have D2, and then we have D1. Do you see how powerful this is? We converted the documents to vectors, and now we compute the dot products, and we just rank them. The higher the cosine, the closer to 1, the higher in the results, and the further away, the lower in the results. Isn't that a great feeling of intellectual satisfaction when you build something like this? I mean, the people who did that are really amazing. So that is called the vector space model when we do that. Is there a question? Or? Oh, yes, yeah, that's true. Yeah, I need to put it very, yeah, exactly. So, yeah. But anyway, yeah, since you agree with me that D5 wins over D4, we no longer need to actually do that. Okay. So you see, AI is not perfect. It's still not able to put that on a screen. All right. And the same goes here. If I have now the other query Q1, then probably D2 comes first, then D1, then D5, then D4, and then D3, right? So now that's very, very powerful what we have here. But here's the thing. It's nice. Mathematically, we are very happy because we designed a system that mathematically works. So at that point, the mathematician just goes home and is happy about what they did because they solved the problem, right? But now comes the computer scientist and say, no, it's not solved yet. It's not solved yet because now we need to implement that. And the problem with the implementation is that we are looking at, sit tight, 1 billion vectors in a Hilbert space of dimension 500,000. And now you want to compute all of these billion of scalar products with 500,000 coordinates. So yes, the mathematician is very happy about that because mathematically it's done, but we need to implement that. But I have good news for you because now you can put your, so leave your mathematician hat and put your computer scientist hat. How will a computer scientist think about that? We have vectors. We have the query on the left and the document on the right with 500,000 coordinates in there. We want to compute the dot product. Now, visualize a query in your head. Now, visualize how the vector of the query could look like. A typical query you would put in Google. What can you tell me about the query vector? Isn't there something particular to the query vector? Could it be any vector, or does it have something typical that might happen to the query vector? Yes? Exactly, it contains almost only zeros. If I give you a vector of 500,000 numbers with no zeros at all, and I tell you that's a query, you're not going to believe me. That's not possible. Nobody puts a query of 500,000 terms. No, actually they do. When you upload a PDF to an LLM, you actually do that. But anyway, if you put a Google query, which is the interest right here, you are going to have a lot of zeros and very few coordinates with non-zeros. For a computer scientist, that's great because it means the scalar product, all the part with the zeros goes away. So we are not actually computing a scalar product on 500,000 coordinates. We are only computing one on 4 if it's a query with just 4 words, right? So that is now simple to do. That we can do, right? So we still have to do it a billion times, but at least each scalar product is only on 4 coordinates, right? So that's progress. We are making progress. So now that we know one scalar product we can do efficiently, let's think of how we actually scale the thing with doing it repeatedly with plenty of documents. So we have this magical formula that gives us the similarity between 2 documents. It's basically the dot product. So we multiply coordinate-wise, and we just need to renormalize by the vectors. Now, I changed a little thing in the formula because here I basically have the scalar product divided by the norms, but I did, even though probably now you master math to a point that you didn't even notice, but actually I moved the renormalization from an absolute renormalization of the total. I moved it inside the sum, right? And that you know because division is distributive over addition, right? So I just moved it over here. And now I just have a sum of this. It's very important because now I'm going to bring that back in the context of evidence accumulation. When I said earlier, we're accumulating evidence by summing things. So that's the direction in which I'm going right now. So we have these terms that we want to add. More exactly, what do I have in there? I told you for the purpose of this lecture, it's the TF-IDFs. So I'm basically multiplying the TF-IDFs for my documents and term, multiplied with my TF-IDFs for the query, and I'm just summing over the terms, right? That's my dot product. Who agrees with that? Okay. And now it's expressed in a big sum over the terms. I just need to traverse and do it for every term, a big sum of all of that. Which brings us now to the implementation, and I'm just wondering if I managed to do it before we go, if there's a big cliffhanger for next week. Now that we look again at the standard inverted index, and we have to compute that, we just need some place to store the pre-computed TF-IDF, right? Because we want to probably, if we want to do evidence accumulation in the way I explained with the intersection algorithm, I need to store it somewhere. It needs to be there. So perhaps, since the TF-IDF depends on a term in a document, and what is a term in document? It's a posting. So we can put a TF-IDF for every blue square in there gets a TF-IDF. The problem here is that it's going to break a few things. First, the compression algorithm that we spent 1 week designing with the beautiful gamma code is gone, because now I basically have to store a real number in there, and you can forget the compression. So there's already kind of a big deal that it breaks a few things. So yeah, we cannot do that because we want to preserve what we've done before. So it would be nice if we just put integers in there instead of floats. Can we put integers? Yes, I could just put my term frequency. That is an integer. That I can still use the gamma code to compress, right? Maybe not with the gaps, but I just lose the gaps, but I can use the gamma code. Who agrees? If I have a list with the document IDs and the TFs, I can use the gamma codes. Okay. But if I put the TF in there, I need to put the IDF somewhere else. That somewhere else is going to be here. Note that the IDF depends on the term, not on the document. So I can factor them out and just store them together with the document frequency, or instead of the document frequency, in there. What is the IDF? It's log of n over df, right? So I can put them in the purple squares. But there is one thing people do. They don't compute the log. They just compute n over df and put it in there. Why? That's a question that many people ask. There's a couple of answers to that. First, log of n over df would be very, very specific to the case that we use TF-IDF as weights. But I told you these are not the only weights out there. There's plenty of other ways of computing the weights. And so you don't know if everybody is going to take the log. Maybe some people will not take the log. So by not computing the log and just putting n over df, you leave it open. Like, people have a choice. They can take the log, they cannot take the log, they do whatever they want. You do not constrain them. Another aspect is that computing the logarithm can be a bit expensive compared to just multiplication and so on. So if you want to avoid the computation of logs, then you don't pre-compute them, and every time the index changes, but you can just do it on the fly at runtime, right? So these are all the reasons. For whom does that make sense? right? So we don't compute the log, just n over df. And the purple rectangles are perfect for that because df, that's what was already in the purple box, right? So now I just take n over that. Okay. And for the query, it's easy. We can just compute it. It's a very small query. Computing the term frequency is very easy. So I will keep now the last piece of the puzzle on how it assembles together to compute the scalar product for next week as a cliffhanger. But I think you probably in your head already have an idea of how this is going to be done. Oh, yes, you're right. Yes, absolutely. Not next week. In three weeks, right? Yes. Oh, we are skipping 3 weeks. That's going to be rough. Okay, so in 3 weeks, that's a big cliffhanger, right? Like cutting a series in the middle for a few months. Okay, but I want to know, just to see, am I too fast? Am I too slow? I mean, I can tell in the lecture, like how many people are asleep. That kind of gives me an indicator, but still it's good to know. So that tells me I'm not too fast, at least. And I'm also not too slow because most of you followed. All right. So that's it. You're free to go. Get some lunch. Do not forget to complete the quiz by 3 p.m. Most of you who took it pass it. If you don't pass, you maybe have still attempts to pass, but that's very, very few who didn't pass. So thank you very much. Enjoy the exercises, enjoy your vacations, and see you in 3 weeks for the continuation. Thank you.